Yeah, so the hope is, I mean, this is not, we don't know this to be true, but it's kind of, again, it's one of the many prejudices that is implied by the principle of compositionality, is this idea that you can, in general, interpret, you can, okay, if we take the linguistic example, so you can imagine having a category, a syntactic category and a semantic category. So you've got a category where the objects are just kind of empty symbols, and your algebra is just it's just specifying, if you like, the grammar for how those empty symbols can be linked together. So you have a thing that just says, verb, adjective, whatever, I don't know. But so you've got some purely syntactical category. There's no meaning there. But then you could imagine defining a semantic category where now it's got the same. Obviously, the grammar is preserved, right? Because once you take the abstract grammar and you imbue the individual components of it with semantic content, the grammar doesn't change. It's just that all you've done is there's new structure there that wasn't there before, but everything else is preserved. And so then you can imagine building a semantic category which has the same compositional properties, but where the objects now have actual semantic meaning. And then the statement that when you imbue the individual morphemes or the individual empty structures with semantic content, the statement that process doesn't change the grammar is the statement that the map between those categories is functorial. And that's the sense in which we say that functoriality, that the map between syntax and semantics, we think is functorial in nature. And so you bring up this work that Xerxes and I did, primarily Xerxes, I should say, but it's so that's an example of a situation where, so the idea, that particular instantiation of this idea is based on the thought that we've got, if you like, we've got algebra, right? We've got algebra which gives us kind of the logic of how how these discrete structures glue together and whatever, and that's like our syntax, that's like our grammar. And then we've got semantics. What is the semantics in physics or in a model of physics? Well, it's these things like geometrical structures, right? So because when we take, say, a causal graph that represents the causal structure of space-time, and we talk about its manifold properties, and we talk about its decomposition into space-like hypersurfaces or whatever, it's like we're taking this purely anonymous syntactical object and we're imbuing it with kind of semantic content. And the semantic content here is topology and geometry. The topology and geometry is not part of the syntactic structure. It's something you impose on top of it that's consistent with it and therefore functorially related to it, but is not implied by it directly. And so the hypothesis was that this is really an instance of this kind of general functorial map between, if you like, the mapping between the algebra of how multi-computations are composed and the semantics of how you, from that, get geometrical structures that you care about in physics. Our hypothesis, Xerxes' central hypothesis was that this is an instance of that kind of functorial transformation between syntactic and semantic categories. And that construction from the paragraph you described is just a particular way of kind of enacting that, right? So the principle there is you say, well, okay, maybe I have to go on a slight diversion about infinity categories, but so the idea is that okay, there's this idea called Grothendieck's hypothesis, which kind of gets to the heart of or supposedly if true, would really get to the heart of what it means for something to be spatial, what it means for something to have spatial structure, to have topological structure. And the idea is that it comes from the following intuition. That's actually quite a nice intuition if you think about it in the right way. So if you've got some space, then you can look at points in that space, and you can look at paths between the points in that space. And if you imagine looking at a pair of points that have two different paths, x and y, between those points, then you could look at the continuous deformations of those paths, the so-called homotopies, right? And if there's like a hole between those points, then there'll be some obstruction, right? There'll be some homotopies you can construct and some that you can't. And so you can imagine constructing what's called the homotopy space, or the homotopy type, which again, as a spatial structure, is another topological space, a higher dimensional space, where now each point in this new space is a path in the old space, and each path in the new space is a homotopy in the old space. And that gives you the sort of first homotopy space, the first homotopy type of the space you started from. And then you can do this construction again. You can construct the homotopy type or the homotopy space of that thing, and go and again and again and again, and you get these progressively higher dimensional structures. And when you do this in terms of categories, if you like, the points are now objects, and the paths are now morphisms, and the homotopies are now two morphisms that build some higher categories. So then the idea is that this gives you a kind of an inductive construction by which you can start from a one category of some topological space, and you build up to an infinity category that is the kind of infinity homotopy type. And then the remarkable thing is that once you've built this big ladder to get up to this infinity category, you can actually kick the ladder away, right? That somehow up to weak homotopy equivalence, the structure of this infinity category, the structure of this infinity homotopy type, completely determines the topological structure of all the spaces below it in this whole infinite hierarchy, which is not true of any of the others, right? All of the others don't have this property. It's something that only happens in the infinite limit. So then Grothendieck said, well, maybe, therefore, we don't need, all we need is infinity categories, right? If somehow if these infinity categories, so from any topological space, you can build up this infinity category that completely determines the properties of that space and all of its homotopy types up to weak homotopy equivalence. Then maybe the correspondence goes in the other direction as well. So maybe it's not just that all spaces can be interpreted as infinity categories, but maybe all infinity categories can be interpreted as spaces by the same construction. So Grothendieck's hypothesis is really this idea that infinity categories and topological spaces are the same thing, that infinity categories are really just a way of thinking about topological spaces in the most general sense. So the idea behind this in this paper was saying, okay, one way we can explicitly construct this functor from, if we think about like the algebra for how processes in quantum mechanics and in general relativity compose together, if we think about that as being like the syntax of physics, and then if we think about spatial structures like spacetimes and Hilbert spaces and whatever as being like the semantics of physics, one way we can explicitly build this functorial map between those two categories is we can start from a multi-way system. We can then introduce these homotopies between the paths to get these progressively higher order multi-way systems until we build up to a Rulio multi-way system that is the concrete instantiation of this infinity category. And then all the lower multi-way systems are then just sections that we take through that Rulio multi-way system. And then, if that's true, and if we take the sections in the right way, then there's a possibility that the reason why, because you might ask, well, why does a multi-way system have a spatial structure? Why would a causal graph have a spatial structure, right? It's a discrete thing, right? Why would we have an interpretation of this in terms of space-time? Well, then, if this hypothesis is really true, then all that's happening is you've got this Rulio multi-way system that has inherited spatial structure from some kind of Grothendieck'ian origin. You take a global section through it, you get an ordinary multi-way system, or you get a causal graph, or you get a hypergraph or something, and then the spatial structure of that causal graph or hypergraph or multi-way system is inherited from the spatial structure of the Rulio multi-way system of which it is a section. And if that's true, that would allow us to explicitly construct this sort of functorial correspondence between the syntactic category and the semantic one. There's much more I can say about this, because I mean, for instance, like one thing that we're interested in looking in the center is this relationship. So I believe, and have believed for a long time, that there's really a deep relationship between semantics and causality, that I think, because when you build a multi-way system, there are many, many different ways that you can equip it with a causal structure, right? Because to equip it with a causal structure, you actually have to know what the individual states and events were to be able to determine whether the events are causally related. So it seems to me that if the multi-way system is like syntax, then the causal structure is a phenomenon of semantics. It's a byproduct of semantics. And my conjecture is that actually it's not just a byproduct, it's the causal structure is the semantics, that you can always reconstruct one from the other. And so I'm one thing that I'm interested in using kind of the sensor's resources to try to investigate is this hypothesis that basically causality and semantics are somehow in one-to-one correspondence. And so, for instance, one project that we're currently working on is trying to do a kind of big inventory of all the different notions of causal semantics that have arisen in physics, in computation, in chemistry, trying to encode them in the most general way using these algebras of concurrent processes and Petri nets and sigma nets and so on, and trying to construct a kind of unified compositional semantics that describes them. Because my hope is that unified compositional semantics will give us a general way of constructing these functors that let us map from syntax to semantics, or to put that in a computational way, for a given multi-way system, allow us to construct what possible causal structures are consistent with that multi-way system and which, and which would be inconsistent, which right now we don't have a way of doing. But I think there is, I think there is there is a formalism by which that can be done, but we haven't invented it yet.
So the hypothesis would be, and correct me, I just want to have a little fun here.
Yeah.
So at the infinity category limit, the syntax is functorially equivalent to potential semantic territory at the infinity category limit.
Exactly. So it's like, so somehow, yeah. So it's like down here when we're scrubbing about at the one category or two category level, it's like the symmetry is broken, right? So syntax and semantics are different things. Mm-hmm. And to take a one category and equip it with semantics, you need to basically equip it with some causal structure that is, in the way we've traditionally formulated it in the context of our project, we've done that by equipping it with a two category structure where the individual morphisms have two morphisms between them that represent causal relations. But yeah, so in a sense, exactly as you say, when you go to the infinity category limit, it's like, well, now you've got all possible higher category structures are inside your infinity category. So it's not just, so you don't just have all possible all possible syntaxes, but you will somehow also have all possible semanticses. And so everything, all the syntax, all the semantics, all the causality that you could ever hope to have should somehow be contained in that infinity category object. And if you take sections in a sufficiently careful way, it should be able to be kind of functorially inherited down. Mm. Yeah, exactly. That's a really nice way to think about it.